Right now, as you read these words, something is passing through your body. Not one thing, billions of things. Particles with mass, particles that have been drifting through the cosmos since shortly after the Big Bang. Particles that outnumber every atom in your body by a factor of 6 to 1. You cannot feel them. You cannot see them. They do not interact with the light in your eyes, the neurons in your brain, or the electrons that carry charge through your nervous system. They pass through the earth itself as though it were made of nothing at all. And here is the part that should keep you awake at night. These particles, this dark matter, make up 85% of all the matter in the universe. Everything you have ever touched, everything you have ever seen, every star in the night sky, every galaxy that has ever been photographed by every telescope humanity has ever built, all of it represents a tiny fraction of what actually exists. We are the minority. We are the exception. We are 5%. The numbers alone should stop you cold. For every atom in your body, there are approximately 6 particles of dark matter sharing the same space. The chair you're sitting on, the floor beneath your feet, the air in your lungs, all of it is outnumbered, outmassed, overwhelmed by something you cannot detect. We have built our entire civilization on what amounts to cosmic table scraps. We call ourselves the dominant species on Earth. We call our science the pinnacle of understanding. We call our universe vast and mysterious. But we've only been looking at 5% of it. And the question that some physicists are now beginning to ask is one that sounds like science fiction, but is grounded in hard physics. What if the other 95% isn't empty? What if it isn't simple? What if the dark sector, that vast, invisible ocean we are swimming through, contains its own atoms, its own chemistry, its own stars, its own planets, and its own civilizations? Civilizations that could be living out their existence right here, right now, in the same space we occupy, separated from us not by distance, but by the fundamental laws of physics themselves. What if there is intelligent life all around us, and we will never, ever know? To understand why this idea isn't as crazy as it sounds, you first need to understand what we actually know about dark matter, and more importantly, what we don't. The story begins in 1933, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of over 1,000 galaxies, about 320 million light-years from Earth. Zwicky measured how fast the galaxies within the cluster were moving, and what he found didn't make sense. The galaxies were moving too fast, far too fast. Based on all the visible matter he could see, the stars, the gas, the dust, there wasn't nearly enough gravitational pull to hold the cluster together. By rights, the Coma cluster should have torn itself apart billions of years ago, its galaxies scattering into the void like drops of water flung from a spinning wheel. But it hadn't. The cluster was still there, bound together by something invisible. Zwicky calculated that there must be about 400 times more matter in the cluster than what he could observe. He called this missing ingredient Dunkelmaterie, dark matter. For decades, the idea languished. It seemed too strange, too convenient, like an accountant inventing a fictional expense to balance the books. But then, in the 1970s, astronomer Vera Rubin and her colleague, Kent Ford, turned their attention to individual galaxies and found the same impossible physics playing out everywhere they looked. Galaxies rotate, stars orbit their galactic centers, the same way planets orbit stars. And according to Newtonian physics, the same equations that let us predict the motions of spacecraft and the timing of eclipses, stars on the outer edges of galaxies should be moving more slowly than stars near the center, just as Pluto orbits the Sun more slowly than Mercury. But they don't. Rubin and Ford measured the rotation curves of dozens of spiral galaxies and found that stars at the edges were moving just as fast as stars near the center, sometimes faster. The implication was inescapable. Something invisible, something massive, something that didn't emit or absorb any light was wrapping around these galaxies like an enormous, invisible cocoon, providing the gravitational pull needed to keep them from flying apart. The dark matter halos that Rubin's work revealed are staggering in scale. The Milky Way's visible disk, the spiral arms you see in photographs, containing hundreds of billions of stars, spans about 100,000 light-years. But our galaxy's dark matter halo extends more than 1 million light-years in every direction. We are not a galaxy that happens to have some dark matter around it. We are a tiny speck of visible matter floating in an ocean of darkness that stretches nearly 10 times farther than anything we can see. A 2014 analysis of stellar motions calculated the dark matter density near the Sun's position in the galaxy to be about 0.009 solar masses per cubic parsec. That might sound like a tiny number, but integrated over the entire volume of the galaxy, it adds up to somewhere between 600 billion and 3 trillion solar masses of dark matter in our galaxy alone, compared to roughly 200 billion solar masses of visible stars. The Milky Way is more dark matter than anything else. By mass, you could say the galaxy isn't really a collection of stars at all. It's a dark matter halo that happens to have some luminous contamination near the center. And this isn't just true of galaxies. It's true of the universe itself. In the modern cosmological model, dark matter is the scaffolding upon which everything visible has been built. After the Big Bang, ordinary matter was too hot, too energetic, too evenly distributed to collapse under its own gravity and form structures. But dark matter was different. It didn't interact with light, which meant it could begin clumping together while ordinary matter was still a seething plasma of particles and radiation. These early dark matter clumps became the gravitational seeds around which galaxies would eventually form. The visible universe we observe today, every galaxy, every cluster, every filament of the cosmic web, exists because dark matter built the framework first. We are not the main event. We are the decoration. We are the thin layer of luminous paint applied to an invisible canvas. The evidence for this picture is now overwhelming. It comes from galaxy rotation curves and cluster dynamics, yes, but also from gravitational lensing, the way dark matter bends light from distant galaxies, revealing its presence through its gravitational influence, even though it emits no light of its own. One of the most stunning pieces of evidence came in 2006, when astronomers observed the Bullet Cluster, 2 galaxy clusters that had collided and passed through each other about 150 million years ago. The collision separated the hot gas from the galaxies themselves, and gravitational lensing revealed that most of the mass, the dark matter, had passed right through, barely affected by the collision, while the gas lagged behind. The Bullet Cluster gave us a direct visual of dark matter's existence, two glowing regions of hot gas offset from two invisible regions of mass, showing that the matter and the mass aren't the same thing. The dark matter kept moving while the visible matter got stuck. Evidence also comes from the cosmic microwave background, the ancient light from when the universe was just 380,000 years old, whose subtle patterns encode the density of dark matter with exquisite precision. The Planck satellite measured these patterns to extraordinary accuracy, finding that dark matter makes up about 26.8% of the universe's total energy content, while ordinary matter accounts for just 4.9%. The remaining 68% is dark energy. But that's another mystery for another time. The cosmic microwave background tells us something else remarkable. Those tiny temperature fluctuations, the seeds that would grow into galaxies, have a specific pattern that depends on how dark matter and ordinary matter behaved in the early universe. The pattern we observe could only arise if dark matter doesn't interact with light. If dark matter scattered photons the way ordinary matter does, the cosmic microwave background would look completely different. The fact that it looks the way it does is proof that dark matter is truly dark, transparent to light, invisible to electromagnetic detection. It comes from computer simulations that can only reproduce the observed structure of the universe when they include enormous quantities of invisible mass. Dark matter is real. This is not speculation. This is not a guess. This is physics. What we don't know, what remains one of the greatest mysteries in modern science, is what dark matter actually is. For decades, the leading assumption has been that dark matter is simple. A single type of particle, perhaps something called a WIMP, a weakly interacting massive particle, that has mass and gravity but interacts with ordinary matter only through the weak nuclear force, if at all. WIMPs are motivated by theories like supersymmetry, which predict the existence of partner particles for everything in the standard model. The lightest of these supersymmetric partners would be stable and would have been produced in the right quantities during the Big Bang to account for all the dark matter we observe. This is the WIMP miracle, the remarkable coincidence that particles predicted by completely independent physics, theories designed to solve other problems entirely, would naturally produce exactly the right amount of dark matter. But here's the thing. We've been looking for WIMPs for 40 years. We've built detectors deep underground, shielded by miles of rock from cosmic rays, designed to register the faint impact of a dark matter particle colliding with an atomic nucleus. The LHX Zeppelin experiment uses 10 tons of liquid xenon. The Xenon T experiment operates beneath Italy's Gran Sasso mountain. The Panda X detector sits beneath China's Jinping Mountains, protected by more than 2 kilometers of rock. None of them have found anything. The sensitivity of these experiments is almost incomprehensible. The Xenon 1T detector could register the impact of a dark matter particle that deposited less energy than the recoil of a single atomic nucleus, an event so subtle that even the radioactive decay of trace impurities in the detector materials could drown out the signal. Scientists had to build these detectors from the most radio-pure materials ever assembled, in the deepest, quietest places on Earth, just to have a chance of hearing the faint whisper of dark matter. They heard silence. We've searched for WIMPs at particle accelerators, too, looking for the telltale signature of missing energy that would indicate dark matter particles being produced in high-energy collisions and then escaping the detector. The Large Hadron Collider at CERN has run experiment after experiment, collision after collision, recording and analyzing trillions of events. Nothing. This decades-long absence of evidence doesn't prove that WIMPs don't exist, but it has prompted many physicists to ask a more fundamental question. Why should dark matter be simple? Why should we assume that 85% of the matter in the universe is composed of just one type of boring, non-interacting particle? After all, ordinary matter isn't simple. Ordinary matter consists of 6 types of quarks, 3 types of charged leptons, 3 species of neutrinos, and all the particles that carry forces between them. Ordinary matter builds atoms from protons, neutrons, and electrons. Those atoms bond into molecules. Molecules form proteins, cells, organisms, ecosystems, civilizations. We are 5% of the universe, and look at the complexity we contain. Consider what ordinary matter has accomplished in our tiny luminous corner of reality, starting from just 3 particles, protons, neutrons, and electrons, bound by just 3 forces relevant at everyday scales: electromagnetism, the strong nuclear force, and gravity. Ordinary matter has produced the entire periodic table of elements. It has built crystals and liquids and gases. It has created chemistry so rich that scientists have catalogued tens of millions of distinct molecules, with billions more theoretically possible. And from that chemistry emerged life, self-replicating molecules, cells, organisms, ecosystems spanning every niche on Earth, from volcanic vents at the bottom of the ocean to clouds in the upper atmosphere. Brains capable of asking questions about the universe that created them. All of this from 5%. All of this from what amounts to leftover cosmic debris. So why should the other 85% be any less interesting? This is the question that drives physicists like Jesse Shelton, a theorist at the University of Illinois at Urbana-Champaign, who specializes in what's called dark sector physics. Her work begins with a deceptively simple premise: dark matter might not be alone. Dark sectors are, by their very definition, built out of particles that don't interact strongly with the standard model, Shelton explains. But that doesn't mean dark sector particles don't interact with each other. Think about neutrinos, Shelton suggests. We are constantly bombarded with neutrinos from the sun. Trillions pass through your body every second, but they interact so weakly with ordinary matter that they might as well not exist, as far as your atoms are concerned. Neutrinos share the same space as everything else, but almost never touch anything. Now imagine an entire sector of particles like that, particles that don't interact with ordinary matter or light, but that might interact with each other through their own forces, their own physics, their own rules. There is no particular reason to expect that whatever is going on in the dark sector has to be as simple as our most minimal models, Shelton points out. After all, we know that our visible world has a lot of rich physics. Photons, electrons, protons, nuclei, and neutrinos are all critically important for understanding the cosmology of how we got here. The dark sector could be a busy place as well. This is not science fiction. This is active research at some of the world's leading institutions. The theoretical framework is straightforward. Extend the standard model with additional gauge symmetries and particle content that don't couple directly to our familiar forces. Add dark photons, carriers of a dark electromagnetic force. Add dark electrons and dark protons that can form bound states under this dark electromagnetism. Add the possibility of dark chemistry. The mathematics works. The physics is consistent. There's no law of nature that says the dark sector must be simple. In fact, string theory, the leading candidate for a unified theory of physics, naturally predicts the existence of multiple hidden sectors. When physicists try to connect string theory to the real world, they find that the equations typically produce not one sector of particles and forces, but many. Our standard model might be just one of numerous sectors, each with its own gauge groups, its own matter content, its own rules. String theory doesn't just allow hidden sectors, it expects them. The resulting picture is what physicists call a rich dark sector or a hidden sector, a parallel world of matter and forces that exists alongside our own, invisible to our detectors, not because it's far away or hidden behind something, but because it simply doesn't talk to our particles. Harvard physicist Lisa Randall, one of the most cited theoretical physicists in the world, has spent years exploring these possibilities. In her research with colleagues like Matthew Rees and her papers on partially interacting dark matter, Randall has outlined how a fraction of dark matter could have rich interactions, while most of it remains simple and collisionless. In 2013, Randall and her collaborators proposed something remarkable. If a component of dark matter could emit dark photons, it would cool and collapse into a thin disk, much like ordinary matter forms the disks of spiral galaxies. This double disk dark matter model predicts that galaxies could have two disks occupying the same space, one of ordinary matter that we can see, and one of dark matter that we can't. The implications were stunning. Randall wrote a book about them, Dark Matter and the Dinosaurs. The title wasn't a metaphor. She proposed that as our solar system oscillates up and down through the galactic plane every 30 million years or so, it might periodically pass through this dark matter disk. The gravitational disturbance could dislodge comets from the Oort cloud, sending them hurtling toward the inner solar system. One such comet might have struck Earth 66 million years ago, ending the reign of the dinosaurs. Dark matter, in this picture, isn't just cosmological background. It's an active player in the story of life on Earth. Her key insight is that we shouldn't assume all dark matter is the same. If we were creatures made of dark matter, Randall writes, we would be very wrong to assume that the particles in our ordinary matter sector were all of the same type. Maybe dark matter is like ordinary matter, mostly simple stuff. Hydrogen makes up most of the visible universe, after all, but with a small fraction that's much more interesting. And that small fraction, that interacting component, could do something ordinary cold dark matter cannot: collapse, cool, and form structures. Here's the problem with standard dark matter. It's boring. Not in a scientific sense. It's endlessly fascinating as a research topic, but in the sense of what it can build. Dark matter, as we understand it, only interacts through gravity. It doesn't feel the electromagnetic force, so it can't emit light or absorb it. It doesn't feel the strong nuclear force, so it can't form atomic nuclei. It just floats. It clumps together under gravity. Yes, creating the enormous halos that surround galaxies. But it can't collapse further. It can't form dense objects. It can't build dark stars or dark planets or anything resembling structure at scales smaller than galaxy halos. The reason comes down to a fundamental feature of structure formation: dissipation. When ordinary matter collapses under gravity, it heats up. A cloud of hydrogen gas falling toward a center gets denser and hotter as gravitational potential energy converts to kinetic energy. If that were the end of the story, the gas would just keep heating up until its thermal pressure halted the collapse, and it would settle into a fluffy, diffuse equilibrium, much like dark matter halos. But ordinary matter has a way out. It can radiate. Atoms emit photons. Energy escapes. The gas cools, loses pressure support, and collapses further. This is how stars form. Through the magic of dissipation, gas clouds can shrink by factors of millions, reaching densities high enough to ignite nuclear fusion. Dark matter, in the standard picture, can't do this. It has no dark photons to emit, no way to shed energy, so it just hangs there, in enormous, fluffy halos, incapable of forming anything denser. This is why astronomers expected dark matter to be smooth on small scales, and for the most part, it is. Dark matter halos around galaxies don't have small, dense clumps the way ordinary matter does. There are no dark matter asteroids, no dark matter planets, no dark matter stars, at least not in the standard model. But the standard model has problems. When cosmologists run computer simulations of galaxy formation using only cold, collisionless dark matter, they find that the predicted structure doesn't quite match observations. The simulations produce too many small satellite galaxies around objects like the Milky Way. They produce dark matter halos with steep density cusps at their centers, when observations suggest flatter, chord profiles. These discrepancies, known as the missing satellites problem and the cusp core problem, have persisted for decades. One solution that James Bullock and other researchers have explored is self-interacting dark matter. Dark matter particles that can scatter off each other, redistributing energy within halos and smoothing out the central cusps. But if dark matter particles can scatter off each other, that implies the existence of some kind of dark force mediating the interaction. And once you have a dark force, you're on the road to richer physics. But what if some dark matter could dissipate? This is where atomic dark matter enters the picture. First proposed in detail by physicists like David Kaplan at Johns Hopkins, and further developed by researchers around the world, atomic dark matter consists of dark protons and dark electrons bound together by dark photons, an exact parallel of ordinary atomic hydrogen, but composed entirely of dark sector particles. If such matter exists, the implications are extraordinary. Dark atoms would cool by emitting dark photons, just as ordinary atoms cool by emitting ordinary photons. This would allow dark matter to collapse further than standard cold dark matter ever could. It would form dark disks within galaxies, thin, dense structures spinning in the same plane as the visible disk of stars and gas. Simulations show that even if atomic dark matter makes up just a small percentage of the total dark matter, as little as 5 or 6%, it could dramatically alter the structure of galaxies. And those simulations show something else too. Something that sounds like it belongs in a science fiction novel, but emerges directly from the physics. Dark atoms could form dark stars. In 2023, a team led by astrophysicist Paul Sutter ran simulations of galaxies containing atomic dark matter. They watched as the dark atoms cooled and clumped, falling toward the centers of dark matter halos. They watched as dark disks formed, and then they watched as the densest regions collapsed further and further until they underwent something that had never been seen in a dark matter simulation before: dark star formation. In the simulation, the atomic dark matter formed dark stars of its own, the researchers reported, and could even trigger the formation of its own black holes. Think about what this means. If even a small fraction of dark matter has atomic-like properties, the universe might be filled with dark, stellar populations, stars that emit no light we can see, that exist in the same galaxies we observe, that might even be orbiting the same galactic centers as our visible stars, but that are completely, utterly invisible to every telescope humanity has ever built. We could be surrounded by trillions of dark stars, and we would never know. The physics of how such stars might form is now being studied in detail. In the visible universe, star formation begins when a cloud of gas becomes massive and dense enough that gravity overwhelms thermal pressure. The cloud contracts, heats up, radiates away energy, and contracts further. Eventually, the center becomes hot and dense enough to ignite nuclear fusion, and a star is born. For dark star formation, the process could be analogous. Dark gas clouds would collapse under dark gravity, heat up from compression, radiate dark photons, cool, and collapse further. The question is whether the dark physics would allow for stable equilibrium configurations, dark pressure balanced against dark gravity, the way our physics produces stable stars. The answer appears to be yes. Simulations by researchers at multiple institutions have shown that atomic dark matter can form gravitationally bound objects with star-like properties. The details depend on the specific parameters of the dark sector, the masses of dark protons and dark electrons, the strength of the dark electromagnetic force. But for a wide range of parameters, dark stars appear to be possible. Some of these dark stars might be tiny, barely more massive than asteroids. Others might be enormous, comparable to our own sun or larger. And some, according to the simulations, might collapse further to form dark black holes, gravitational singularities in the dark sector, invisible except for their gravity. We would see none of this. The dark sector would have its own stellar populations, its own cycle of star formation and death, its own cosmic evolution, and we would be completely blind to all of it. But the possibility that has most captured physicists' imaginations goes even further. If dark matter can form atoms, and dark atoms can form stars, then in principle, dark atoms could form chemistry. The chemistry we know, the chemistry of life, depends on the electromagnetic force allowing atoms to share electrons, forming bonds, building molecules of staggering complexity, carbon chains, amino acids, DNA, proteins. The entire machinery of biology emerges from the physics of atomic bonding. If dark atoms exist, governed by a dark electromagnetic force, then dark chemistry becomes possible. Dark molecules, dark macromolecules, and if the conditions are right, dark life. Lisa Randall confronts this possibility directly in her writing, with the intellectual honesty of a physicist who knows how far out on a limb she is climbing. Shadow life, exciting as that would be, won't necessarily have any visible consequences that we would notice. making it a tantalizing possibility, but one immune to observations, she writes. In fairness, dark life is a tall order. Science fiction writers may have no problem creating it, but the universe has a lot more obstacles to overcome. The obstacles are real and significant. We don't know what conditions are required for life beyond the chemistry we're familiar with. We don't know if dark electromagnetism would produce the right kind of binding, the right energy scales, the right diversity of molecular configurations. We don't know if dark stars would have the right properties to host habitable planets, or if dark planets would even form in the first place. Life as we know it requires an enormous coincidence of physical constants. The strength of the electromagnetic force has to be just right to allow stable atoms. The masses of protons and neutrons have to be nearly equal for nuclear physics to work. The energy levels of carbon have to align precisely with helium and beryllium for stars to forge heavy elements. Change any of these by a few percent, and chemistry as we know it becomes impossible. Would the dark sector have similar coincidences? Would dark chemistry produce the kind of molecular diversity that allows for information storage, replication, and evolution? Would dark environments have the right temperatures, the right energy sources, the right raw materials? We simply don't know. But here's the thought that keeps some physicists up at night. The dark sector is big, really big. It contains 5 times more matter than our sector. And if the parameters of the dark sector are even slightly different from ours, different masses, different force strengths, the probability calculations for dark life could be completely different from the calculations for visible life. Maybe dark chemistry is easier than ordinary chemistry. Maybe dark self-replication is simpler. Maybe the conditions for dark life are more common than the conditions for visible life. Or maybe they're impossible and the dark sector is sterile. But we also don't know that any of this is impossible. And here's the thing that makes this more than idle speculation. The dark sector, if it's rich, is much bigger than our sector. 85% of all matter potentially forming its own atoms, its own molecules, its own structures. If life has even a small probability of emerging from chemistry, and if dark chemistry is possible, then the dark sector might contain far more life than the visible universe ever will. We might not be searching for dark life. Dark life might be everywhere, and we're just not equipped to see it. At Oak Ridge National Laboratory in Tennessee, physicist Leah Broussard is conducting experiments that sound like they come from another universe, because, in a sense, that's exactly what she's looking for. Broussard is searching for mirror matter, a hypothetical form of dark matter that would be an exact duplicate of ordinary matter, with mirror particles corresponding to every particle we know, but interacting only with itself through mirror forces. Her experiments send beams of neutrons through magnetic fields and toward barriers that ordinary neutrons cannot penetrate, looking for evidence that some neutrons might oscillate into mirror neutrons and back again, passing through the barrier while in their mirror state. The idea behind these experiments is that there might be a tiny mixing between ordinary neutrons and mirror neutrons, a quantum mechanical overlap that allows one to sometimes become the other. It's similar to how neutrinos oscillate between their different flavors, or how neutral kaons mix with their antiparticles. If neutron-mirror-neutron oscillation exists, it would be the first direct connection between our sector and the mirror sector. So far, the results have been inconclusive. Some experiments have found hints of anomalies that could be explained by mirror neutrons. Others have found nothing. The search continues. The mirror matter hypothesis is older than most dark matter theories, dating back to a 1956 paper by physicists Tsung-Dao Lee and Chen-Ning Yang. The idea is simple. What if there's a mirror copy of the standard model with mirror electrons, mirror protons, mirror photons, interacting among themselves just as our particles interact among themselves, but invisible to us because our photons don't talk to their particles? In such a picture, the mirror sector would have had the same physics as our sector in the early universe. Mirror nucleosynthesis would have produced mirror hydrogen and helium. Mirror gas clouds would have collapsed to form mirror stars. Mirror stars would have forged mirror-heavy elements and scattered them into mirror space through mirror supernovae, and then, presumably, mirror planets would have formed around mirror stars, some of them in mirror habitable zones, with mirror liquid water on their surfaces. If mirror matter exists, there could be an entire mirror universe overlapping with our own. Mirror galaxies occupying the same space as our galaxies. Mirror stars interspersed among our stars. Mirror planets orbiting where our planets orbit. And mirror people standing in mirror rooms writing mirror articles about whether their dark sector, which is us, might contain life. Zurab Beregiani, a physicist at the University of L'Aquila in Italy, has spent years developing this picture. He suggests that dark matter and mirror matter might be the same thing, that the dark matter halos we observe gravitationally are really collections of mirror matter, matter that has its own light, its own stars, its own worlds, but whose photons don't couple to our eyes. Dark people is probably a bit far-fetched, admits Broussard when discussing Beregiani's work. But dark matter is very likely as rich as our own matter. This kind of thing needs to be explored. There's a more recent theory that pushes these ideas even further. In 2024, physicists proposed that our universe might have a CPT symmetric counterpart, a mirror universe running backward in time from the Big Bang, populated by antimatter and existing before our universe began. The idea emerges from one of the deepest symmetries in physics. CPT symmetry holds that if you reverse charge, flip spatial orientation, and reverse time simultaneously, the laws of physics stay the same. Our universe appears to violate this symmetry. It's made of matter, not antimatter. It has a particular spatial handedness. It runs forward in time. But maybe that's because we're only seeing half the picture. In this model, proposed by Latham Boyle at the Perimeter Institute and collaborators, the Big Bang wasn't a beginning. It was a mirror. On our side, time runs forward, matter dominates, and we evolve toward ever greater complexity. On the other side, time runs backward from our perspective. Antimatter dominates, and an entire universe evolves in a direction we would call before. The mathematics of this theory is elegant. It starts from a simple premise. The universe should respect CPT symmetry, not just in its local laws, but in its overall structure. Our universe alone doesn't seem to. It has a definite arrow of time. It's made of matter rather than antimatter. It has a particular handedness. But if you include the mirror universe, the combined system is perfectly CPT symmetric. Every asymmetry on one side is balanced by the opposite asymmetry on the other. One striking prediction of this model concerns dark matter. If the CPT symmetric universe exists, it would naturally contain right-handed neutrinos, the mirror partners of our left-handed neutrinos. In our universe, we only see left-handed neutrinos, which has always seemed strange. Why should nature play favorites? The CPT model explains it. Our universe has left-handed neutrinos because the mirror universe has right-handed ones. The combined system is symmetric. These right-handed neutrinos in our universe would be stable, massive, and invisible to most experiments. They would behave exactly like dark matter. The two universes would never meet. They would never communicate, but they would both be real, and both would contain everything. If this picture is correct, and it remains highly speculative, then there isn't just dark matter forming structures around us. There's an entire antimatter universe running backward through time, potentially just as complex as ours, potentially containing its own version of life, potentially containing beings wondering whether their dark sector hides civilizations too. The philosophical implications are dizzying. We might not be alone in the universe. We might not even be alone in our own location in space-time. But the barriers between us and any other intelligences might not be mere distance. They might be fundamental physics, separating us more completely than any gulf of space ever could. Let's return to something concrete, something we actually know. The James Webb Space Telescope has been observing objects in the early universe that don't quite make sense. Some of the most distant galaxies appear too massive, too bright, too developed for the time when they existed. Standard models of galaxy formation struggle to explain how such structures could have formed so quickly after the Big Bang. In July 2023, a team led by Cosmin Ely at Colgate University, in collaboration with Catherine Fries at the University of Texas at Austin, proposed an explanation. These objects might not be ordinary galaxies at all. They might be supermassive dark stars. Dark stars, in this context, don't mean stars made of dark sector particles. They mean stars made mostly of ordinary hydrogen and helium, just like normal stars, but powered by dark matter annihilation, rather than nuclear fusion. The theory works like this. In the early universe, the first stars formed within dense clumps of dark matter. If dark matter consists of particles that can annihilate when they collide, converting their mass to energy, just as matter and antimatter do, then those early stars would have had an extra heat source. The annihilation energy would have puffed the stars up, preventing them from collapsing to the densities needed for nuclear fusion. The result would be enormous objects, perhaps millions of times the mass of the Sun, that could shine for billions of years without ever igniting hydrogen fusion. When they finally exhausted the dark matter fuel in their cores, they would collapse directly into supermassive black holes, potentially explaining the mysteriously large black holes observed at the centers of early galaxies. This is one of the biggest puzzles in modern astronomy. We observe quasars, enormously bright objects powered by accreting supermassive black holes, at such early cosmic times that there shouldn't have been time to grow black holes that massive through normal processes. Black holes grow by swallowing matter, but there are limits to how fast matter can fall in. Even if a black hole ate as fast as physically possible, starting from a stellar mass seed, it would take longer than the universe was old to reach the masses we observe. But if dark stars formed in the early universe and grew to millions of solar masses before collapsing, they would create supermassive black hole seeds directly, skipping the slow accumulation process entirely. For the first time, we have identified spectroscopic supermassive dark star candidates in JWST, ILI reported in 2024, including the earliest objects at redshift 14, only 300 million years after the Big Bang. The objects in question: JDIS GS-Z 13-0, JDIS GS-Z 12-0, and JDIS GS-Z 11-0, were originally classified as early galaxies. But their properties are unusual. They're extremely bright for their distance. Their spectra show features that could be consistent with enormous puffy stellar atmospheres, rather than collections of smaller stars. They might not be galaxies at all. They might be individual objects, single dark stars more massive than 1 million suns, shining with the light of dark matter annihilation. If confirmed, this would be our first detection of dark matter's influence on individual stellar objects, rather than on the scale of entire galaxies. It would be evidence that dark matter isn't just scaffolding. It's an active player in cosmic evolution, and it would open the door to questions we're not ready to answer. If dark matter can power stars, what else can it power? What structures might have formed in the early universe that we've never even imagined? James Bullock, a physicist at UC Irvine and one of the world's leading experts on galaxy formation and dark matter, has spent years developing computer simulations to understand how dark matter shapes the cosmos. His work has led him to a striking conclusion. The standard picture of dark matter as simple, non-interacting particles might be wrong. There is no particular reason, Bullock has noted, that dark matter should be as boring as astronomers tend to assume. Bullock's simulations explore what would happen if dark matter particles interacted with themselves, not with ordinary matter, but with each other. The results are dramatic. Self-interacting dark matter produces galaxies with different density profiles, different shapes, different substructure than standard cold dark matter. And intriguingly, self-interacting dark matter seems to match observations better in some cases, particularly for small dwarf galaxies where standard models have struggled. The implications extend beyond fixing anomalies in galaxy rotation curves. If dark matter interacts with itself, it might form bound states. It might have its own forces, its own radiation, its own thermodynamics. It might, as Bullock puts it, be as rich as our own matter. The question is no longer whether the dark sector could be complex. The question is whether it is complex, and if so, how complex. And here's what makes this question so profound. We might already have the answer, hidden in data we've already collected. The anomalies in galaxy rotation curves that led to the discovery of dark matter might contain signatures of dark sector complexity. The unexplained features of dwarf galaxies might be telling us that dark matter interacts with itself. The impossibly large black holes at the centers of early galaxies might be the remnants of dark stars. The evidence might be there, waiting for us to know what to look for. Physicists are now combing through decades of astronomical observations, searching for hints that they might have missed the first time around. They're looking for gravitational signatures that could indicate dark structures. They're looking for unexplained perturbations in stellar orbits that could reveal the presence of dark objects. They're looking for anything that doesn't quite fit the simple picture of cold, collisionless, dark matter? The answer might already be in the data. We just haven't known how to read it. At CERN in Switzerland, the Search for Hidden Particles experiment is preparing to sail into the unknown, approved by the CERN Research Board and scheduled to begin operations in 2031. SHIP will send high-intensity proton beams into a target, hoping to produce particles from the hidden sector, particles that interact so feebly with ordinary matter that they've escaped detection until now. The experiment is designed to catch particles with long lifetimes, particles that travel tens of meters before decaying into something detectable. Among the particles SHIP hopes to find are dark photons, axions, and heavy neutral leptons, hypothetical particles that could connect our visible world to a vast dark sector we've never touched. Meanwhile, at Fermilab in Illinois, the dark SRF experiment is using superconducting radio frequency cavities to search for dark photons with exquisite sensitivity. The experiment traps ordinary photons in one cavity and looks for evidence that some of them transform into dark photons and back again, a quantum oscillation that would reveal the existence of an entire hidden electromagnetic sector. The dark SRF experiment recently achieved unprecedented sensitivity in the search for dark photons. Using cavities cooled to temperatures near absolute zero, where electromagnetic energy flows through niobium without resistance, the researchers were able to detect potential dark photon signals that would have been completely impossible to observe with any previous technology. In July 2023, they published results putting the world's best constraints on dark photon existence in certain mass ranges. The dark photon is a copy similar to the photon we know and love, but with a few variations, explained Fermilab researcher Ronnie Harnick. If dark photons exist, they would provide the first concrete evidence that the dark sector has its own electromagnetic-like force, the foundation upon which dark atoms, dark chemistry, and potentially dark life could be built. At Jefferson Lab in Virginia, the Heavy Photon Search experiment collides electrons with tungsten targets, hoping to produce dark photons that would decay into electron-positron pairs. The experiment looks for small bumps in the invariant mass spectrum, statistical excesses that would indicate new particles being created and immediately destroyed. The ADMX experiment at the University of Washington searches for axions, another dark matter candidate, using powerful magnets that might convert axions into detectable photons. The Ice Cube Neutrino Observatory at the South Pole watches for neutrinos produced by dark matter annihilation in the sun's core, where dark matter particles might accumulate and occasionally meet and destroy each other. And at laboratories around the world, physicists are developing new techniques to probe the dark sector directly. Gravitational wave detectors might one day sense the mergers of dark stars or dark black holes. Pulsar timing arrays might detect the gravitational influence of dark structures passing through the galaxy. Precision measurements of ordinary atoms might reveal tiny deviations caused by dark matter interactions. We are entering an era where the dark sector is no longer purely theoretical. It's becoming experimental. We're building the tools to reach into the darkness and see what's there. But here's the thing that should truly unsettle you. Even if we detect dark matter particles, even if we map out the entire particle content of the dark sector, even if we confirm that dark atoms and dark chemistry and dark complexity exist, we might never know if dark life exists. Because here's what that complexity means. If the dark sector has its own physics, its own forces, its own ways of building structures, then whatever exists there would be invisible to us in a more fundamental way than anything we've ever contemplated. We can't shine light on dark structures because they don't interact with our photons. We can't send probes to dark planets because our probes are made of ordinary matter that passes right through. We can't receive signals from dark civilizations because any dark photons they might broadcast would pass through our detectors without a trace. The only connection between our world and theirs would be gravity, and gravity, as forces go, is phenomenally weak. The electromagnetic force holding the atoms in your body together is about 10 to the 36 power times stronger than the gravitational force between them. You can hold a magnet in your hand and overcome the entire gravitational pull of the Earth. This means that even if dark matter formed dense structures right next to us, dark stars, dark planets, dark cities, we would feel only the faintest gravitational tug. We might notice statistical anomalies in the motion of distant stars. We might infer that something massive is passing nearby, but we would never see what it was, never touch it, never communicate with it. There could be dark beings occupying the same room you're sitting in right now, going about their dark lives, thinking their dark thoughts, and you would never know. Not because they're hiding, not because they're too far away, but because the laws of physics themselves have drawn a boundary that neither of you can cross. This isn't just speculation. This is what the physics allows. Consider what it would take to detect a dark civilization. They would have to emit something that interacts with our matter. But if their matter only interacts through gravity or through forces so weak we haven't measured them yet, their emissions would pass right through any detector we could build. It would be like trying to catch neutrinos with a butterfly net. Even if dark beings figured out how to manipulate gravity to create gravitational waves, say, as signals, the waves would be so weak as to be undetectable across any meaningful distance. The gravitational waves we detect from merging black holes, events that release more energy than all the stars in the observable universe combined, barely wiggle our detectors by a fraction of a proton's width. No civilization, no matter how advanced, could produce gravity waves strong enough to carry detailed information between worlds unless they could somehow manipulate stellar masses. And there's no reason to think a dark civilization would even want to communicate with us. Why would they? They wouldn't know we exist. We'd be invisible to them, just as they'd be invisible to us. Their scientists might speculate about whether a visible sector exists, a strange realm where matter interacts with something called light, but they'd have no way to test the hypothesis. Two sectors, same space, forever separate. This is, in a sense, the ultimate expression of cosmic loneliness. We have spent decades searching for extraterrestrial intelligence, pointing radio telescopes at the stars, sending golden records into interstellar space, calculating the Drake equation with various optimistic and pessimistic assumptions. We worry about the Fermi paradox. Why, if the universe should be teeming with life, haven't we detected any? The standard answers to the Fermi paradox are sobering. Maybe the evolution of intelligence is extraordinarily rare. Maybe civilizations tend to destroy themselves before they become capable of interstellar communication. Maybe the distances between stars are simply too vast for meaningful contact. But there's another possibility we've never seriously considered. What if the Great Filter isn't a filter at all? What if it's a wall, a boundary built into the structure of reality itself, separating sectors of existence that can never interact? We look at the universe and see mostly emptiness, vast gulfs of vacuum between stars, even vaster between galaxies. We conclude that if other minds exist, they must be far away. But distance might not be the issue. 95% of reality might be teeming with minds, structures, civilizations, all within arm's reach, but forever untouchable. The darkness isn't empty. The silence isn't absence. We're just not equipped to hear. What we can do is imagine. What we can do is wonder. What we can do is recognize that the universe we see is not the universe that is, that there are depths to reality we haven't plumbed, might never plumb, but that exist nonetheless. That recognition, that humility, that awe, that might be the beginning of a new relationship with the cosmos, not as masters or explorers or conquerors, but as participants in something far larger than ourselves, something we share with whatever else exists, even if we can never know what that something else might be. But what if the answer is not that life is rare, but that most of it exists in a sector of reality we cannot access? What if the great silence isn't because we're alone, but because we're trapped in a tiny luminous bubble, surrounded by an ocean of dark life that has no way to speak to us and no way to hear us speak? The visible universe contains roughly 2 trillion galaxies, each containing hundreds of billions of stars. The numbers are already overwhelming, but they represent only 5% of reality. Multiply by 17, and you begin to glimpse the scale of what we might be missing. And the irony is that dark matter made us. Its gravitational scaffolding allowed galaxies to form, stars to ignite, planets to coalesce, life to emerge. We owe our existence to the dark sector. We are, in a very real sense, parasites living in the interstices of a vast dark structure that predates us and surrounds us and will outlast us. The universe was never ours. It was always theirs. Or maybe neither. Maybe the universe belongs to no one. Maybe existence simply is what it is. Multiple sectors, multiple physics, multiple possibilities, all coexisting in a reality far stranger than any single mind could imagine. We're not owners of the universe. We're not even tenants. We're more like echoes, ripples on the surface of something vastly deeper. But we're echoes that can ask questions, ripples that can wonder, and that, perhaps, is the most remarkable thing of all. Of course, we don't know that any of this is true. We don't know that the dark sector is complex. We don't know that dark atoms exist, or dark stars, or dark chemistry, or dark life. These are possibilities, not certainties. They are the questions physicists are asking, not the answers they have found. But consider this. A century ago, we didn't know that dark matter existed at all. We thought the visible stars were all there was. We thought the Milky Way was the entire universe. We were wrong about almost everything. 50 years ago, we thought we understood the basic structure of matter. Then we discovered quarks and gluons, and the weak nuclear force, and the Higgs boson. The Standard Model grew from a few particles to 17, with interactions and symmetries we hadn't imagined. 25 years ago, we discovered that the expansion of the universe was accelerating, driven by something we still can't explain, dark energy, making up another 68% of reality that we cannot see or touch or understand. Every time we've thought we understood the universe, we've been humbled. Every time we've thought we'd reached the edge of discovery, we've found new depths of mystery. The pattern is unmistakable. Each generation of scientists has thought they were close to a complete understanding, and each generation has been proven wrong by discoveries that revealed entirely new layers of reality. Newton thought he had physics figured out, until Einstein showed that space and time were flexible. Einstein thought quantum mechanics was incomplete, until experiments proved him wrong about the nature of reality itself. We stand at another such moment. We know dark matter exists. We know it dominates the matter content of the universe. But we don't know what it is, and we don't know what it does, and we don't know what it contains. The dark sector is the next frontier, and frontiers, historically, are larger than we imagine them to be. Why should this time be any different? Why should we assume that the 95% of reality we cannot see is simple, boring, empty? Maybe the lesson of dark matter is not just that there's more out there than we thought. Maybe the lesson is that out there isn't even the right way to think about it. The dark sector isn't distant. It isn't hidden behind something. It's here, right here, woven through the same space we occupy, running parallel lives in a parallel physics. We are not alone in the universe. We might not even be alone in our own location, but we might never meet. We might never speak. We might spend eternity passing through each other, two worlds occupying the same coordinates, but separated by something deeper than space, something deeper than time, separated by the very laws that make existence possible. There's a strange comfort in this idea, if you turn it a certain way. We have always feared the silence of the cosmos, the vast distances between stars, the cold vacuum, the billions of years of evolution that might never produce another mind capable of wondering at the night sky. We have feared being alone. We've imagined that if aliens exist, they might be hostile. They might come to conquer or destroy. We've worried about announcing our presence to the universe, worried about what might hear us. But the dark sector suggests a different kind of possibility. Life might be everywhere, but fundamentally inaccessible, neither hostile nor friendly, simply separate. The universe might be filled with minds, but those minds might be permanently quarantined from each other by the very physics that allows them to exist. This isn't a comforting thought in the traditional sense, but there's something almost peaceful about it. The universe might not be cold and empty. It might be warm and full. We just can't reach what's in it. And maybe that's okay. Maybe parallel existence is still existence. Maybe knowing that the dark sector might contain beauty and complexity and thought, even if we can never confirm it, changes something about how we see ourselves. We are not the only game in town. We are not the universe's only attempt at meaning. Even if we can never prove it, we can imagine it. And sometimes imagination is its own kind of connection. But what if we're not alone? What if the universe is absolutely teeming with intelligence, just not in the form we expected, not in the place we looked? The dark sector, if it is complex, would be its own kind of miracle, its own testament to to what physics can create when left to its own devices. Dark atoms forming under dark forces, dark chemistry building dark molecules, dark evolution, if such a thing is possible, producing dark minds capable of dark thoughts, dark art, dark science, dark wonder. They might look up at their dark sky, if they have eyes, if they have a sky, and see their dark stars scattered across dark space. They might wonder whether they are alone. They might build dark telescopes and search for dark life on dark planets. They might calculate their own dark version of the Drake equation and wonder why the dark universe is so quiet. And they would never know that we exist, that 5% of reality, a tiny luminous froth on the surface of a vast dark ocean, managed to produce eyes and brains and questions, that somewhere in that strange bright visible sector, beings made of light and charge and nuclear fire are staring into the darkness, wondering if anyone is staring back. The separation between us would be absolute, but the parallel would be perfect. Two versions of existence, both beautiful, both complex, both wondering, both alone, both real. There's a philosophical concept that has haunted human thought for centuries. Solipsism, the idea that only your own mind can be known to exist, that everything else might be illusion. We've generally dismissed solipsism as an intellectual dead end. We behave as though other minds exist, even if we can't prove it from first principles. But the dark sector raises a new version of this ancient puzzle. It's not that other minds might not exist. It's that other minds might exist in such a way that we could never, ever know. Not because of any limitation of technology or distance or time, but because of the fundamental structure of physics. If dark civilizations exist, they would be more isolated from us than anything we've ever imagined. No signal could pass between us, no trade could occur, no war could be fought, no ambassador could be sent. The separation wouldn't be a matter of not having discovered each other yet. It would be permanent, eternal, built into the equations of the universe. What does it mean to share existence with minds you can never contact? We have no category for this relationship. They wouldn't be aliens exactly. Aliens are foreign, but they share our physics, our space, our time. They're theoretically reachable. The dark sector isn't foreign. It's parallel. It's here, but unreachable. It's real, but unprovable. If dark life exists, then we live in a universe where consciousness has emerged multiple times in multiple sectors with no possibility of ever knowing about each other, each thinking they might be alone, each looking at what they can see and concluding that the visible universe is all there is. The dark sector might not just contain civilizations. It might contain civilizations asking the exact questions we're asking, looking for the exact answers we're looking for, failing to find evidence of other minds for the exact same reasons we're failing. Parallel wonderings, parallel isolations, parallel existence. This is the universe as physics now allows us to imagine it. Not a single story, but two stories, or perhaps infinitely many stories, running in parallel, intersecting only through the faintest whisper of gravity, forever isolated by the fundamental structure of reality. We have been telling ourselves a story about the cosmos for as long as we have been capable of stories. First, it was a story about gods and spirits. Then it was a story about mechanisms and laws. Then it was a story about relativity and quantum mechanics, about 11 dimensions and vibrating strings. Now it might be time for a new story. A story about sectors. A story about parallel existences, parallel physics, parallel possibilities. A story about a universe that is not one thing but many things, woven together by gravity but otherwise independent, each sector following its own rules, building its own structures, perhaps producing its own minds. This story isn't proven. It might never be proven. The dark sector might be empty, simple, sterile, nothing but a sea of identical, non-interacting particles drifting through space until the heat death of the universe. But it might not be. And the mere possibility, the physical, mathematical, scientific possibility that we share our reality with other forms of existence we can never contact is enough to change how we think about our place in the cosmos. We are 5%. We are the exception. We are the minority report of existence, luminous and temporary, built on dark foundations we will never fully understand. And somewhere in that vast darkness, life may be flourishing. Civilizations may be rising and falling. Questions may be asked and answered and asked again. Love may exist. Art may exist. Science may exist. All of it invisible to us, separated by something deeper than distance, more permanent than time. The dark sector is real. What it contains is unknown. And that unknown might be the most important thing about our universe that we will never understand. We will never see them. We will never hear them. We will never touch them. But they might be there, right now, right here, passing through us as we speak. Dark neutrinos streaming through our bodies at the speed of light. Dark atoms bound by dark forces, locked in dark molecules, perhaps even organized into dark structures we would recognize as life if we could see them, which we can't. The universe might be a crowded place. The loneliness we feel, staring up at the night sky, might be an illusion born of limited perception. The silence might be full of voices, speaking languages we cannot hear, in frequencies we cannot detect, through media we cannot measure. 5%. That's what we are. 5% of matter, locked in our luminous bubble, looking out at a darkness that might not be dark at all. They might be looking back. They might be asking the same questions. They might be writing the same scripts, telling the same story of isolation and wonder and the strange sadness of being alone. Or maybe they're not alone at all. Maybe the dark sector has already found its dark neighbors. Maybe dark civilizations have already made contact with each other, built dark federations, created dark internets spanning dark galaxies. Maybe the dark sector is teeming with communication and connection, while we luminous creatures float in our isolated bubble, thinking we're the only ones. We'll never know. That's the profound, unsettling, somehow beautiful truth. Whatever exists in the dark sector, whether it's simple particles or complex chemistry or wandering minds, we will never know for certain. But we can imagine. An imagination, reaching across the unbridgeable gap between sectors, might be the closest thing to contact we'll ever have. All around us, in the dark,